morning, everybody. Hope you all had a good weekend. So do know that your test is open. I don't know if anybody's taken it yet. Let's see. I've got one person who's taken it thus far. Okay. No worries, I would be the same way as well. Wait until the end. So you have until today, midnight, to finish up your test, so make sure you do that. We're going to be moving on to chapter 6, 7, and 8, which I would say that this section is usually the most challenging. I'm muted. Really? How about now? Doesn't like it? Still muted? Can't hear me? No. Harley's been able to hear me. Let me see what's... Okay. You can hear me, Lyric. Okay, cool. So it looks like Suzanne stepped out for a minute. Maybe she'll check back in and be able to get in with us. All right. So can you hear? Awesome. Cool. So yeah, this section here, I think is usually the most cumbersome for students. Like they tend to be like, this test tends to be the one that's like, oh gosh, there's a lot of math. So if you don't like math, it can be a little bit challenging, and there's a lot of concepts, but we're going to try and go over stuff a bunch of times. I'm going to try and give you a bunch of practice problems so that we can go through it step by step and hopefully make it relatively accessible. Let's share screen here. Can you hear me? Okay. Oh, and I do have, I don't have the link on me. I'll bring it on Wednesday. A course evaluation link that you can fill out, which would be great. If you can let me know how the course has been going, feedback, maybe feedback on me personally, or feedback on just online in general. That can also be useful for us to know what is and isn't working. Okay, chemical compositions. When we're looking at sodium, hello. When we're looking at sodium, sodium is a mineral that we need to consume daily in order to regulate our body fluids. But we don't want to eat too much sodium because it can lead to high blood pressure and other issues. We don't eat sodium though, because that is a highly reactive metal. So we receive sodium by consuming sodium chloride, which is table salt. So we need to present our body with sodium through sodium chloride. The FDA recommends that we consume somewhere less than 2.4 grams of sodium per day, which is 2,400 milligrams of sodium. Now, the important thing is that the mass of the sodium that we need is not the same thing as the mass of the sodium chloride that we actually eat, right? The amount of sodium chloride is going to be something greater than 2.4 grams if the sodium itself can max out at 2.4 grams. So how many grams of sodium chloride are you actually allowed to consume and still be in the recommended dose for sodium? Well, there is a way to figure it out using your formula unit, so NaCl. We get 1 sodium for every 1 sodium chloride. We know the masses of sodium and chlorine are different, so it's not enough to just say, oh, well, just take the total and cut it in half, right? Because this atom weighs more than this atom does. Chlorine is much heavier. So we will need to figure out how much of each there is, and then from there, go ahead and calculate the sodium. So this is sort of the gist of what we're going to be doing throughout this whole chapter, is hopping around from formulas to individual elements, or from one formula into a different formula, all sorts of things like that. So the information in a chemical formula can be combined with atomic and formula masses to calculate how much of a constituent element is in a compound. So looking at this, how much iron is given in a certain amount of iron ore, and the iron ore would probably be like an iron oxide, or how much chlorine is in chlorofluorocarbon. So being able to figure out the constituent element from the full elements amount. So in order to do this, we've got to do a little bit of a, we have to move a little backwards and talk about, and this is going to seem weird, but talk about nails, okay? So when you go to a hardware store, if they have like loose nails and stuff like that, they don't sell the nails by counting the individual nails. That would take forever. Instead, they'll have some sort of scale, and you'll scoop the nails up and get a weight of the nails. And then there'll be some sort of conversion between the weight of the nails and how many nails there are. So maybe, you know, for every pound of nails, you're getting 150 nails. Why don't they just count the nails individually? Because they'd be there all day counting nails, and they don't make enough money off of nails in order to do that. Now, this is a similar problem with counting like atoms. So if I have carbon, for instance, I've got a little container of carbon here. I'm not going to count up the carbon atoms and say I've got 6.62 times 10 to the 28th carbon atoms, because that will take me for all eternity. So instead, we weigh the amount of carbon that we have. So in this case, we've got 8.25 grams of carbon. Now, we can go from the mass of our nails back into the amount of nails, and we can also go from the mass of carbon back into the amount or number of atoms as well of the element. If we look at this conversion factor or this conversion problem here, this is bringing it, this is looking at the nail portion. So if a customer buys 2.6 pounds of medium-sized nails, and this says a dozen nails weighs 0.15 pounds. How many nails did the customer buy? Okay, so I know what a dozen nails equals. A dozen nails equals 0.15 pounds. That right there is a conversion factor. So you start with your given information, which is how many pounds we have. So we have 2.6 pounds of nails. And because of the conversion factor, we know that every dozen nails is equal to 0.150 pounds. Why do I put the pounds on the bottom? So that it'll cancel out with my given pound unit. Now we'll be in a unit of dozens of nails, but it doesn't say, hey, how many dozens of nails? It says, how many actual nails do you have? So we're going to go one step further and use the relationship that a dozen nails equals 12 nails. All right, so for every 1 dozen nails, we get 12 nails. The dozens will cancel, and you end up with 208 nails. Now, could it be 209 nails? Could it be 207? It could. That's our best estimate of what it is. So conversion factors will definitely be coming back, but you've got some new conversion factors. All right, so when we're counting atoms, we're not going to count the atoms. We're going to weigh the material and work backwards to figure out how many atoms there are. Just like we don't count the nails, we weigh the nails, and then we work backwards to figure out how many nails are actually there. Same thing is true with atoms. We have to measure its mass. We don't even have the option to count the atoms because they're so small and they're so numerous that if you were to count them for 24 hours a day, forever and ever, you'd never get through, you know, a grain of sand's number of atoms. But in the now analogy, we used 1 dozen. A dozen is not going to do it for counting atoms because that's only a magnitude of 1, right? We're going from 1 to 12. So we need something that is a dozen, but sort of like a dozen on steroids. And they call this the chemist dozen, and it's known as the mole, M-O-L-E, short M-O-L. We don't shorten this to M. Its abbreviation is not M. M would be meter, okay? So a mole is equal to 6.022 times 10 to the 23rd individual whatevers. All right, so if I have 1 mole of carbon, that is equal to 6.022 times 10 to the 23rd carbon atoms. Now, hopefully you can see how this is like a dozen, but on steroids, because look at what the magnitude is. It's 10 to the 23rd. So this is a huge relationship as opposed to 1 to 12. So sometimes we refer to this as Avogadro's number. And it states that 1 mole of anything is equal to 6.022 times 10 to the 23rd units of that thing. So let's say I had a mole of marbles. I wouldn't have a mole of marbles ever, but if I did have a mole of marbles, it would be equal to 6.022 times 10 to the 23rd marbles. It's a lot of marbles. 1 mole of sand grains corresponds to 6.022 times 10 to the 23rd sand grains. Again, this number is so large, it's not something we use with everyday objects. Instead, it's going to be something we use with microscopic things or subatomic. And if you're wondering, okay, well, what is, I get a mole is 6.022 times 10 to the 23rd individual atoms, but like, what does that mean? Is that like really big? Is it really, is it the amount of a planet? Is it the amount of, you know, something really small? Well, it's sort of falls within a reasonable size or like everyday human size. So a mole of copper atoms is about 22 pennies, something like that. A mole of helium atoms is about 2 balloons. So when I'm saying, hey, I've got a mole of something, it's something you could hold in your hand or carry in your arms, okay? It's not something really, really large. And so why is it 6.022 times 10 to the 23rd? Well, it's based off of a standardization of carbon. So if I'm looking at carbon-12, the isotope carbon-12, and I'm looking at exactly 12 grams of it. So we're assuming carbon-12 has an AMU of 12. If we're looking at exactly 12 grams of it, it should by definition have 6.022 times 10 to the 23rd atoms in it. So there we go. That's where it came from. So this thing is nice because it gives us a relationship between counting and weighing, right? So I can say, hey, I have 3.5 moles of this thing. How many atoms are there? Because we're not going to want to count the atoms up. So let's say we have 3.5 moles of helium. Okay, let's do that. Okay, so we're given that we have 3.5 moles of helium. And I want to find how many helium atoms this is. Okay, so we're looking for a relationship between moles and atoms. The relationship between those two is 1 mole of helium is going to be equal to 6.022 times 10 to the 23rd helium atoms. Now, sometimes you'll see people use 6.02 times 10 to the 23rd. That's fine as well. So here's our relationship. So we start with our given. We have 3.5 moles of helium. And I want to go into atoms. So if mole is here, I need to put mole on the bottom. 1 mole of helium is equal to 6.022 times 10 to the 23rd helium atoms. Now I want you to actually plug this into your calculator, okay? Because I don't want anyone to have issues with exponents while they're calculating. And if you are having issues with exponent, we can get it cleared up here as opposed to you getting it cleared up after you take the test and see why you got it wrong, okay? So in this instance, moles will cancel. We're going to take 3.5 times 6.022 times 10 to the 23rd. Now, let's talk about what's going on with your calculator. If you can find the EE button, that is going to be your best bet. So what it would be to plug this into your calculator, this thing here, we would go 6.022, you'd hit the EE button, 23. Don't EE 1020 to the 23, just hit 6.02 EE 23. So we'll take 3.5 times 6.022 EE 23. Again, if you're using, like me, you're slacking and you're using your cell phone calculator, okay, turn it to the side if you've got an iPhone. It'll expand it out and you'll see the EE sitting right next to the number 1. So I like using this EE button. I like setting it up like this in my calculator as opposed to this, because when I set it up like this, it locks this in place. It preserves that as like a chunk. So I know that if this happens to be under a fraction bar, I don't have to like use additional parentheses. If this is under a fraction bar, you will have to use additional parentheses because otherwise your calculator will multiply the first, or rather divide the first one and multiply the second one. So when we spin this into our calculator, I've got 2 sig figs. So I'm going to just use 2 sig figs. So 2.1 times 10 to the 24th helium atoms. Anybody having trouble with that in their calculator? Anybody getting 10 to the 23rd or 10 to the 25th? That's a common mistake. We'll be off by 1 factor. Okay, I'm going to give you 1 more of these. And I want you to solve it. So let's say you're given that you have 12.8 moles of H2O. I want you to find H2O molecules. Okay, so in this instance, we're talking about water molecules. You can still use that relationship. It's going to change just slightly in that we're going to say 1 mole of water is equal to 6.022 times 10 to the 23rd water molecules. Because remember, a mole of anything is equal to the most sort of elemental part of it. So 12.8 moles of water. And we want to go into molecules. So for every 1 mole water, we're going to get 6.022 times 10 to the 23rd water molecules. Okay, this will cancel with this. Plug it into your calculator, and we should get 7.7 times 10. Well, 7.71. I'm going to give it 3 sig figs because I gave 3 sig figs. times 10 to the 24th. Water molecules. So if you didn't like scientific notation, well, you're gonna want to get used to it, because we definitely don't want to be writing these numbers out in full decimal notation. It'll drive you crazy. So we're gonna want to get comfortable with these ideas of times 10 to the. Let's go in the other direction. Okay, so let's say instead of giving you moles, I give you number of atoms. So we have, given that we have 3.14 times 10 to the 22nd silver atoms. And that number is just so cumbersome that I want to know what it is in moles. So find moles of silver. So I'm going to have you do that. You'll use the same relationship. You're just going to have to tweak the direction. Okay, so here we're going to start with a given amount of the individual particles. 3.14 times 10 to the 22nd silver atoms. Now I'm going to use my conversion factor of 1 mole of anything is equal to 6.022 individual things. I want moles though, so I'm going to put the 1 mole of silver on top, and we relate this using Avogadro's number, 10 to the 23rd Ag atoms. So the Ag atoms will cancel and we'll be left with moles. This is where you may want to put 6.022 EE 23 into your calculator, because when I write it this way, I don't have to put the parentheses in if I'm not doing that. This, anything that's above the fraction bar, you can just sort of plug in. But if it's below the fraction bar like this, you need to make sure you're putting parentheses around this whole unit, because otherwise what the calculator is going to do is what you tell it to do. If you just plug in 3.14 times 10 to the 22nd divided by 6.022 times 10 to the 23rd, due to order of operations, it is going to take this number, multiply it by this number, which is good. It's going to divide it by this number, but then it's going to multiply it by this number. Okay, and that's going to give you a very, very, very large number. So we want to make sure that we preserve this as a unit value. So when we plug that in, what did I get here? I ended up with 0.0521 moles of silver. So does anybody have any questions on going from moles to individual amounts or individual like particles into moles? That's where we're going to use Avogadro's number. I'm going to make like a big flow chart thing, and we're going to add to it throughout the, clear this out. We're going to add to it throughout the lecture. So I'm going to put number of atoms. And then over here, I'm going to put moles of element. And we're able to go back and forth between these two by using Avogadro's number, Avo's number. Okay. I'm also going to put number of molecules. And moles of compound. This is like when we did the water one. And we can also get back and forth between these two using Avogadro's number, Avo's number. We're just going to leave this here because we're going to add some more stuff to that. All right, so we've talked about what a mole is, and a mole is like a dozen on steroids. But looking at these two pictures, I just want to make note, a dozen large nails and a dozen small nails are going to have a different weight, right? Why? Because a dozen large nails are large and a dozen small nails are smaller. So the value of the small nails should be, the mass of it in grams should be lower. This is true for moles of, say, iron versus moles of helium. They're going to have a different mass. Let's look at what that is. So 1 mole of sulfur weighs 32.06 grams. 1 mole of carbon weighs 12.01 grams. Think if those numbers are sounding familiar at all. All right, grab your periodic chart and take a look at what the mass on the periodic chart of sulfur is. The AMU averaged mass is, what do you know, 32.06, okay? So those numbers are not just telling you how heavy an atom is, it's also giving you this value called a molar mass. Molar mass meaning the amount of mass in any 1 mole of the material. So looking for instance at copper, the copper atom has an atomic mass of 63.55 AMUs. So what that is saying, in addition to that, is that 1 mole of copper weighs 63.55 grams, or the molar mass of copper is 63.55 grams per mole. There's an inferred 1 underneath the division bar to let us know that this is per every 1 mole. Oh, look at that. 2 different units related to each other. It is a conversion factor. So now we're going to be able to layer this on, and actually we can hop from moles of a certain amount into grams and vice versa. Now just be mindful that when we're talking about the relationship between grams and moles of a material, the value will change. It's based off of what its mass is on the periodic chart. But when we're going from moles into individual atoms or molecules, that value does not change. The relationship is 6.022 times 10 to the 23rd. The lighter the atom is, the less 1 mole of it will weigh. So look at your periodic chart, and you can't really tell me, but in your mind, tell me, what is the molar mass of bromine? So find a peak on your periodic chart, look up bromine. Now bromine is number 35, but we don't use the 35 value. That's the number of protons. We're going to use its atomic mass. So bromine should have a molar mass of 79.904. Cesium. Cesium's a pretty heavy one. It's over in the lower left-hand corner. Cesium has a molar mass of 132.905. How many decimals should you use when you're working with these? I'd say like 2 to 3 if you can. You're going to see certain ones that I round off, like oxygen. is 15.9994. I just call that 16. Okay. Hydrogen, 1.007. I usually round that to 1.01. So 0.58 grams of carbon. Okay, yeah, so let's do that. Oh, we can add some more to our chart here. So up here where the elements are, I'm going to put grams of the element. So now I can go between moles of an element and grams of an element using molar mass. And in parentheses, put periodic chart. Okay, we get that information off the periodic chart. So we're given that we have 0.58 grams of carbon. And I want to find the moles of carbon because grams aren't doing it. So in this instance, when you're going from grams to moles, looking at our flow chart that we have up here, our master flow chart, we're going from this thing, grams, into this thing, moles. So I need to use molar mass. This is dependent on what the material is. So in this instance, my molar mass for carbon is 12.011 grams per mole. We can also write this as 12.011 grams of carbon for every 1 mole of carbon. The mole value is always given the 1. The numerical portion always sits with the gram. So we have given 0.58 grams of carbon. And I'm going to use my molar mass as a conversion factor. So if grams is on top here, I'm going to put the gram on the bottom. 12.01 or 12.011 grams of carbon is equal to 1 mole of carbon. The grams will cancel and we just plug it in. So in this case, 0.58. We get 0.048 moles of carbon. Let's say we're given, I'm going to have you do this one, given 136 grams of iron. I want you to find how many moles of iron that is. Okay, so for this one, we're no longer talking about carbon, we're talking about iron. So we need to figure out the relationship or the molar mass of iron. And so in iron's case, it has a molar mass, which is equal to 55.845 grams per mole. So start with our given, we have 136 grams of iron. I want to go into moles. So for every 1 mole of iron, the 1 always gets attached with the mole, the numerical value gets attached with the gram. So 55.845 grams of iron. Those will cancel. I don't think about, oh, when I'm going from grams to moles, I divide. When I'm going from moles to grams, I multiply. I just set it up in dimensional analysis and let it remind me how I need to enter it into the calculator. So 136 divided by our 55.845. And I see that there's a comment in there. I'll grab it in just a sec. 2.44 moles of iron. How do you type in your calculator? Oh, you got it. Okay, good, Lyric. I'm gonna have you do one more going the other direction. So let's say that you're given, you have 19.2 moles of barium. I want to find how many grams of barium that is. Moles to grams. So set that up in your dimensional analysis and then solve. So really the only difference with this compared to the previous ones, besides it being about a different element, barium, is that we're going in the other direction. You're given moles and we want to find grams. So we still need our molar mass here. So 1 mole of barium is equivalent to 137.327 grams of barium. So I'm trying to write it in some different ways. Up top a little farther, in some different ways, grams per mole or mole equals gram. So conceptually, hopefully you can understand that relationship. So we start with our given 19.2 moles of barium. And in this case, I want to go from mole to grams. So I'm going to put the 1 mole of barium on the bottom. And then I'm going to put its mass value on the top, 37.327 grams of barium. Now, when you're dealing with like oxygen that has 15.99, that can be rounded to 16. But if you have something like this, right, that's got like a 3 or a 5, don't round that to 138. Okay, keep the decimals for that. So the moles will cancel, and we end up with, I get 3 sig figs. So 2 grams of barium. A couple other ways that this could be written. Sorry, this is a comma. Sometimes my commas can look like this. I could write this as 2.64 times 10 to the third grams of barium. That's just this number in scientific notation. Or I could get rid of grams and give it a prefix and say that this is 2.64 kilograms of barium. All these things say the same. So you can change using prefixes or exponents. So now there is a way, actually, like we can take this even a step further and do a twofer. So do 2 jumps in a given problem. So in this case, if I've got, let's say I'm going from grams, I have 0.58 grams of diamond, and for whatever reason, I want to know how many atoms are in that of carbon. I can go from grams of my material into moles of my material, and then moles of material into number of carbon atoms. And we've got a similar thing set up on that flow chart. So if we look up here, we can go from grams into moles, moles into number of atoms, or vice versa. So let's do one of those. Give us a new problem. Let's say that we're given we have 202.6 grams of gallium. And I want to find how many gallium atoms that is. I want you to set that up. I will scroll down a little bit here so we can see our flow chart. And I'll give you a hint. We're starting here, right? Number of gallium atoms, and we want to go over here. Or I'm sorry, we're starting at grams of gallium, and we want to go over here to number of gallium atoms. So we've got to hop through moles. Sometimes moles is called like the crossroads in chemistry because you always have to go through it to get to something else. So there's no way to go directly from grams to atoms or atoms to grams. So I'll give you a couple minutes for that. So for this one, we're going to need to do 2 steps. First, we need to go from grams of element into moles of element, and then moles of element is going to get us into number of atoms. We start with 202.6 grams of gallium. In order to convert this into moles, I need to use the molar mass. So 1 mole of gallium is equivalent to 69.723 grams of gallium. Now, some people sort of stop there, solve, and then do the next one. I'm just going to chain them together. So now if I want to go from moles of element into number of atoms, I can use the relationship that 1 mole of gallium is equivalent to 6.022 times 10 to the 23rd gallium atoms. Grams cancel, moles eventually cancel, and we're left with just gallium atoms. Just a second. So 202.6 divided by, so anything on the bottom is a divider, 69.723 times 6.022 to the 23rd. I end up with a value of 1.75 times 10 to the 24th gallium atoms. Just to give us the practice, let's go in the other direction. So we're given that we have 5.5 times 10 to the 26th rubidium atoms. I want to know how many grams of rubidium this is. So go ahead and set that up using your flow chart. In this case, you're going from atoms back towards grams. And if you have any questions, please ask. You can turn your mute off and ask, or throw it in the chat so that we can just make sure. I want this to feel simple, or as simple as we possibly can make it. Okay, so for this one, we're going from our atoms. So we have 5.5 times 10 to the 26 rubidium atoms. And I want to go into grams. I can't go directly into grams. I have to stop off at my mole crossroads. So 1 mole of rubidium in relationship to its atoms is equal to 6.022 times 10 to the 23rd rubidium atoms. And then from here, 1 mole of rubidium, so it'll cancel there, is equivalent to the mass of rubidium, which is 85.468 grams of rubidium. Mole ends up going away and atom ends up going away as well. And then this one I got a relatively large number, which I expected because I know Avogadro's number is 10 to the 23rd, which will give me a mass value within like a, 1 to 300 grams. So in this one, it's 10 to the 26. So I know it's going to be 2 magnitude or 3 magnitudes higher. So if I ended up getting 78,000 grams of rubidium. Again, you could write this in a couple different ways. We could write it as 78 kilograms of rubidium, moving the decimal over 3, or 7.8 times 10 to the 1, 2, 3, 4, 10 to the 4th grams of rubidium. Just knowing that these things are saying the same thing. On an exam, you may solve for this and say, here's my answer. And the answer is showing up like this, and you're thinking, wait, my answer isn't on there. Where's my answer? It's there. It's just using a different prefix. So how is that feeling so far? Going from grams to moles, moles to atoms, hopefully cool. Hopefully that, I'm just trying to make it as easy as possible. Cool. Yeah, thanks, Harley. Because I know sometimes this mole concept can be like, what is this? I've never heard of this before. So I'm going to try and keep it as simple as possible. Okay, let's go back to the slides. See where we're at. I think we're at. Okay, yeah, cool. Counting molecules. So for elements, the molar mass is really quick to find. You just look at the periodic chart and you figure out whatever its mass is its molar mass. For compounds, you have to do a little bit more work. The molar mass for a compound is 1 mole of the molecule, or 1 formula unit of it. That's because the formula unit component is because ionic stuff doesn't contain individual molecules. It makes that lattice structure. We convert between the mass of a compound and moles of the compound by calculating how much a molecule weighs. How do we calculate the molar mass of a compound? Well, we just add up whatever it contains, we add up the individual amounts. So if I've got like water, H2O, I'm going to take the mass of 2 hydrogens and we're going to add it to 1 oxygen. So let's do that. Let's take the molar mass of water. So molar mass for elements is really easy. You just pull it off the periodic chart. If we're calculating molar mass of an element, or rather molar mass of a compound like H2O, I need to take the mass of hydrogen, which is 1.01, and I need to multiply it by 2. Why 2? Because there's 2 there. I also have oxygen, which is 16, and I'm going to multiply that by 1. So This ends up being 2.02. This ends up being 16. I'm going to add these two together and I get 18.02 grams of water in every mole. So I'm going to give you one to do. You do need to take into account the subscripts. So what is the molar mass of Al2O3? Okay, I want you to find out molar mass of that guy. All right, so for this one, we're dealing with aluminum and oxygen. All right, so I've got aluminum and I've got oxygen. Aluminum has a molar mass of 26 point, what are you, 998, 26.98. And I've got two of them, so I'm going to multiply that by 2. And I've got oxygen, which is 16, and I've got 3 of those. All right. And then I'm going to add those two components together. So 26.98 times 2 gives us 53.96. This gives us 48. You don't have to write it out. Sorry, let me equal that. You don't have to write it out like this every single time. You start to get more comfortable. You can just sort of plug the values in. I'm just doing it so you can see what the aluminum stuff is giving us, what the oxygen stuff is giving us, and then how we're adding those two together. And we should end up with 101.96 grams of Al2O3 per mole. I'm gonna give you one more, because why not? So find molar mass of calcium phosphate. I guess it's not really a question, it's more of a command. So there. Find molar mass of calcium phosphate. If you're wondering, where is the formula? Well, I didn't give you the formula, I gave you the name. So this is a little bit of practice on the exam that you're gonna be taking later on. So first find the formula and then go for it. Okay, so in this one, we've got calcium phosphate. So we have to write a correct chemical formula for it. What I don't want you to do is just go, oh, calcium, that's this thing, and phosphate is this thing. Done. Okay, why is this wrong? Because it isn't charged balance. So calcium, we need to take into account that it has a 2+ charge. Phosphate, PO4, has a 3- charge. From there, we're going to flip-flop. So it should be calcium, the 3 gets dropped down here. Phosphate, PO4, the 2 gets dropped down here. So I should have the mass of calcium times 3, the mass of phosphorus times 2, and the mass of oxygen times 4 times 2 times, which will give us 8. So it's a relatively heavy molecule. So when all these things get calculated and you add them together, you end up with 310.18 grams of Ca3PO4, 2 for 1 mole. Any questions on this one? If you are not sure how to go from here to here, I would recommend doing some studying before you take the next test, okay? Because that's the nomenclature part. All right, so I think we'll pause there for a second. Well, let me just fill in the flow chart. We won't do any more example problems, but let's just fill in here. We can add another box. So in this case, we can go from grams of compound into moles of compound by using molar mass, specifically of the compound. Okay, and I'm going to put in parentheses, you calculate. Right, you've got to calculate it. So next time we're going to talk about hopping between things like this and this, or this and this, or this and this, because we can go from individual elements into compound or compound individual elements. And we'll leave it at that for today. Good luck. If you haven't voted, go out and vote. I already have 3 close people that I know who've never voted in their lives, one of them being 45, who voted for the first time last week. So if you haven't voted before, go do it. There's a lot of people doing it. You can register and vote at the same time at those early voting stops. Okay, enjoy the rest of your day. If you don't need me, sign off. If you do need me, hang around. Bye, guys.